Okay, today we're going to go over the second derivative test, which can be used to find the concavity of a function or the relative extremas, and also, I suppose, the absolute extremas. Um, so first, let's go over what concavity is. It's simply the curvature of a function at a certain point. So if a function was shaped like this, for instance, where the hump is faced upwards, then this is called concave down because the concavity is pointing down. Likewise, we also have a concave up function that looks like this, and the concavity is pointed upwards. So how does this relate to what we're learning? Well, like I said earlier, we can find extrema by using the second derivative test, and you may notice that this point right here at the top of this concave down function is a relative max. And similarly, this over here is a relative minimum. So keep that in mind because there may be questions asking you to find concavity rather than relative extrema. Okay, so if you want to find the concavity, or sorry, the extrema using the second derivative test, what you first must do is find the critical points by setting f prime of x equal to 0. And you'll be given the x coordinates of the critical points, and then you're going to want to differentiate at that x coordinate. You're going to differentiate the function, then plug in the x coordinate, and if the x coordinate is less than 0, then there's a relative max at x. So let me plot this. Relative max means the function looks like this. This is because if f of x is less than 0, then the velocity must be decreasing around the certain point. Let's say this is the certain point. Then the velocity, the slopes are decreasing, I should say, around this point. And that's why if f double prime of x is less than 0, then that's why there's a relative max. If f double prime of x is greater than 0, such as this, as you can see, this is going to be our relative minimum. Let's call that point C. You can see around C, the slopes are increasing. And that is why this is considered a relative minimum. However, if f double prime is equal to 0, then that doesn't prove anything besides the fact that the test has failed. And how does this relate to concavity? Like I just showed on this first one, if f double prime of x is less than 0, you're going to end up with a relative max, which means, well, you can notice, hopefully, that this is concave down because the concavity is facing downwards, which means that if f double prime of x is less than 0, then not only is there a relative maximum at x, but it's also concave down at x. However, if, let's say, f double prime of x is greater than 0, and that not only means that there's a relative minimum, as you can see here, but it's also pointing upwards. The concavity is, which means there's also it's also concave up at this point, and this means nothing because, as I said earlier, if f double prime of x is equal to 0, then it's inconclusive. Okay, so this is example problem 1. It's telling us that there is a point f of 1, which is equal to 8, f prime of 1, which is equal to 0, and f double prime of 1, which is equal to -6. It's asking us to find what type of relative extrema there is at f of 1. We can tell that this is eligible for the second derivative test because f prime of 1 is equal to 0. If you'll remember earlier, I said that you must find the critical points, and then from there you can take the derivative of the function for the second time and plug in those critical points, which means that this test is only eligible for x values at which there's a critical point. And you can see here, since this is equal to, or since f prime of x at this index is equal to 0, then this is a critical point, and that's why we can use this test. So only if f prime of x is equal to 0 at a certain position is that point eligible for the the second derivative test. And even then, it still might not work because you could end up with f double prime of x equaling to 0. However, it does work because you can see that f double prime of 1 is equal to -6. And if you'll recall, if a function, a function, when derived twice, is less than 0 at a certain index, then that means the function is going to look similar to this relative maximum here, meaning that there's clearly a relative maximum at f of 1. Okay, so this is example problem 2. It's asking us to determine the concavity of f if f of x is equal to cosine x, and we want to find it at x equals 0. So first thing we're going to do first, we're going to find the derivative of f of x, which in this case is going to be negative sine of x. Pretty simple. However, now we must determine if this is a critical point. So we plug in 0 for x. Oh god. Sorry, we plug in 0 for x, for f prime of x, and we end up with 0, which means that this is a critical point. So we can take the double derivative of x, and we can see that it's equal to negative cosine of x. And we can plug in our x value once more, this time for the double derivative of f of x, and we end up with -1. So what does this mean? This means that we have a relative maximum, which means that the concavity is pointing downwards, which means f of 0 is concave down. Okay, so this is the final example problem. We want to find the relative max of f of x, where f of x equals x cubed minus 2x squared plus 4. So first we're going to try to find our critical points, if there are any. We're going to do that by finding the derivative of f of x, which is equal to 3x squared minus 4x. From here, we're going to set this equal to 0. And we end up with 0 equals 3x x minus 4/3. And if this statement were to be true, x would have to be equal to 0 and also 4/3. So now that we have our now that we have our critical points, we have to find the double derivative of x, which in this case is going to be 6x minus 4. And now we can plug in our critical points. So we have to find what f double prime of 0 is, which in this case is going to be -4. And we're going to have to find what f double prime of 4/3 is, which in this case is going to be 4. So you can see that f double prime at 4/3 is greater than 0, which means that is a minimum because the slope around it is increasing. However, at f double prime of 0, we end up with a maximum because the slopes around it are decreasing. So the relative maximum of f of x is f of 0.